Welcome to Efiwe, excellence without stress.
Hi guys, we are back again. My wonderful Efiwe's, my smart, my good, my great Efiwe's. We're back on our journey, and today we're going to another topic in physics, which is equilibrium of forces. Forces and their equilibrium. An object is said to be in equilibrium when the resultant force acting on it is zero. When the resultant force acting on it is zero, that is, it has no acceleration. You know what acceleration is? Acceleration is velocity over time. So no acceleration. When the body is said it has no acceleration, then the body is said to be in what? In equilibrium. When the body is in equilibrium, since it has no acceleration, it is either at rest, moving with constant speed in a straight line, not rotating at all, or rotating at a constant angular velocity. So forms of equilibrium, we have the dynamic or kinetic equilibrium. This is when a body is moving with a constant velocity in a straight line or rotating with constant angular velocity. A common example of dynamic equilibrium is a car moving with constant velocity, and we have a ceiling fan rotating with a constant angular velocity. Those are examples of dynamic or kinetic equilibrium. Then we have the static equilibrium. This is where a body is at rest. For an object to be considered to be static equilibrium, it should satisfy these two conditions. One, the net force acting on the object is zero. And two, the net torque acting on the object is also zero. A book at rest on top of a table and a balance seesaw are examples of system under static equilibrium. So we've talked about the static equilibrium. Then resultant and equilibrant forces. The resultant R is a single force that acts alone to have the same effect in both magnitude and direction as all other forces acting together. It's just like one force that has the same magnitude and direction of all the other forces acting together. So the equilibrant E of two or more forces is a single force which will balance equilibrant all other forces taken together. It is equal in magnitude but opposite in direction to the resultant force. You can see the equilibrant equal in magnitude but opposite in direction. So that is the resultant and the equilibrant. A resultant is a single force. This is the resultant that acts alone to have the same effects. These are different forces that act alone to have both magnitude and direction as all other forces. You can see all other forces acting together. This resultant, these two forces acting together, this resultant is having the magnitude of both of them acting together. So the equilibrant of two or more forces is a single force also, which will balance all other forces taken together. It will balance all other forces. It is equal in magnitude to the resultant but opposite in direction. Resultant of forces. How do we resolve forces? We have different forces. We can have two forces. We can have more than two forces. Sometimes the forces will be in right angle. Sometimes they will be in acute angle, and sometimes they will be in a parallelogram. So to find the resultant of two forces, we can apply the parallelogram law that states that if we place two vectors so that they have same initial point, you can see the same initial point, and then complete the vectors with a parallelogram. Look at this. This is vector. You know a vector by direction. So this is the vector, this is the head, this is the tail, head and tail. So you complete them. Then complete the vectors into a parallelogram. Then the sum of all the vectors is directed diagonal that starts at the same point as the vectors. So if you want to get the resultant of this force that have the same starting point here, then this is how to solve it. A plus B, this is A, right? This is B, plus 2 multiplied by A and B cos the angle. This is the angle theta. The angle theta between them. So giving force F1 as 5 and F2 as 7 and angle theta. We are going to go to our board to do that. So look at that. We have it that the square R is the square root of A, B plus 2AB cos theta. Let's go to our board. So this is what we were saying. We have two vectors, right? We have two vectors because we are trying to resolve the vectors. So have one. With the resultant is just one force acting like the two of the forces together. So this is the two forces. Let me delete this one. So we have it. This one is coming. They will have the same starting point. That is how to get them. Then this is it. So this is their starting point, right? So what do? We balance it up. So this is their resultant. So this place is a theta because they have the same starting point as the angle. So that will be A. So the resultant R is just going to be the square root. Okay, this place is A, this place is B, and this is angle theta. Will be A plus B plus 2, A multiplied by B, cos what? Cos theta plus theta. That's what we are saying. Let's check this question we were given. We were given what? 5 and 7 Newton. 5 and 7, and the angle was sister. Sorry, A square, B square, not A. That was a. So A square, B square. Then we're given this place as 5. 5 and 7. Okay, so 7 here. We have 7 here. And the angle was 60. So if we put it into the resultant, we have it as the square root of what? 5 square, right? Plus 7 square plus 2 multiplied by what? 7. 5 times 7 cos what? Cos 60. And that is how to resolve this vector. Two vectors having the same starting point. Then you use the parallelogram law. A square plus B square plus 2AB cos theta will give us our answer. To give us our answer, and the R is 5 square plus 7 square. And you know, you do your normal mathematics and you will get your answer. From our calculations, we had what? The answer was what? The square root of 109. So the square root of 109 is going to give us what? Is going to give us our answer. So we have resolved that vector. So that's what it said. To find the resultant of two vectors, we can apply the parallelogram law, which says that if we place two vectors so they have the same initial point and then complete the vectors into a parallelogram, then the sum of the vectors is directed diagonal that starts at that same point as the vectors. And we have done this to explain that. Don't worry, we are going to do some other ones. Resultant of force. So we have the Lami's theory states that when 3 forces acting at a point in equilibrium, then each forces is proportional to the sign. So A is going to be divided by sine A, B divided by sine B, and C divided by sine gamma. So each force is proportional to the sine of the angle between the other two forces is equal to that. So A sine alpha is equal to B sine beta is equal to C. So when we have 3 forces acting at a point in equilibrium, then the forces is proportional to the sine of the angle between the other two. Then we have the triangle law of forces. According to triangle law of forces, the resultant is equal to the vector sum of the individual forces in any system of forces acting on a particle. This means that if you have 3 vectors acting on an object, the resultant, you can represent them visually as vectors and use the triangle law of forces to find the resultant forces. So let's just quickly solve some questions on resolving. So we have 2 forces. You know forces by their direction. This is the direction of it. So we have this first one, 41 and 60, right? And we have theta. This one is like a perpendicular, is a 90 degree, is at an angle 90 degree. So we are going to use the Pythagoras theorem. This is at an angle 90 degree. We are going to use the Pythagoras theorem. I'm going to use the Pythagoras theorem. So let's go to our board to do that. So we have 41 and what? 41 and 60. We can do any other one. So if you have 2 forces now, you have 2 forces like this, and maybe this one is 5 and this one is 4. This is the direction of the forces. So don't forget that this one too. So this is their resultant. Don't forget this place will also be 5. This place will be 4. So since it's inclined at 90 degrees, you can use the Pythagoras theorem to get the resultant. And how will you get that? You remember that R square will be equals to what? 5 square plus what? Plus 4 square. So R square will be equals to what? 25 plus 16. 25 plus 16. And what's 25 plus 16? R square is going to be equals to 41. So R is just the square root of 41. So you have gotten the resultant because they are inclined at 90 degrees to each other. Then if you want to get the, vectors have what? Magnitude and direction. So what we just got here is just the magnitude. So we have to look for the direction. So the direction is just the tan, because this place is theta and this is going to be opposite over. So direction is just equals to what? The tan, and that's going to be equals to 5 over 4. That's tan theta is equals to 5 over 4, and that is the direction for the one that is inclined at 90 degree. The one inclined at 90 degrees. So let's go to this last one. Another type, more than 2 forces. These ones are more than 2 forces. More than 2 forces. Let's try to draw that. So we have this one that is more than 2 forces. We have a force here, we have a force here, we have 1. So how do we resolve this type of force? How do we resolve this type of force? So we have 50, 75, 50. We have 50 here, Newton. We have 75 here, Newton. And we have 50 here, Newton. So we have 3 forces, right? And 30, 45. So this place was 30. This place was 45, and this was what we were given. So for these vectors now, just understand that each vector has 2 things. They have magnitude and they have direction. And that's what you have to look for. But this type of forces that are more than 1, you have to check them in both axes. You have to check them in both axes. So look at it now. I have y a. This is positive y, right? This is what? Negative y. This is x, positive x, sorry. And this is negative x. So this is what is going to help us in resolving this type of vector. Just remember that all the vectors here, they have vertical component and what? Horizontal component. So horizontal is the x-axis, vertical is the y-axis. So you have to resolve both vectors into the horizontal and the vertical. So if you want to solve this one, we're going to have horizontal component and the vertical component for each of the forces. Then we have it. So we have the forces. What are the 3 forces we have? We have the 50, right? We have the 30, and we have 50. So these 3 of the forces, 50 first for the horizontal component. Is it along the positive x-axis or along the negative x-axis? As you can see, 45 is here. This is the positive x. So it means this is going to be positive. So what are we going to use? And for the horizontal, we use the cos. The vertical, we use what? We use sine. So here we just be what? The angle, which is 75. That will be 75 cos 45 degree. That is not going to be a negative sign. So we have to go again to the vertical component. This same angle 75, is it in the positive y-axis area or in the negative y-axis? Oh, it is in the positive. So it's just also going to be 75 sine what? Sine the same 45. So we go to the next force, which is 30. This is where 30 is. So 30 for the horizontal, is it in the positive side of the horizon of x or the negative side? So what are we going to have? We're going to have minus 50 cos what? 30 degree. Cos 30 degree. Then for the y-axis also, is it the positive y-axis or the negative? It's still positive because this is the positive side. So that one will not carry a negative. It will just be 50 sine 30. 50 sine 30. So we go to the other side, which is the 50 Newton, the last one. Now this 50 Newton is here, right? So to the vertical, have you seen it? You can see that it's 90 degree. So that will be what? 50 cos 90 for the x-axis because it's along the positive x-axis. Then minus 50 what? Cos 90. Why? Because it is along the negative for the y-axis. Don't forget, it's only the angle that is inclined to the horizontal that we use. If you were given a force that looks like this and they put it here and they told you that this place is 30 and they gave you the force 40, you don't use this angle. What you do is you have to deduct 90 from 30 to give you this point, which is going to be what? 60. And that is what you are going to use as the angle. You must only use the angle what? That is inclined to the horizontal. So if you were given anything, if you were given this place as 40, not that you are not going to use that 40 because it's not inclined to the horizontal. You have to use what? 40 minus 90, which is going to give you your 50 degree. So what do? Whatever we have here, with our calculator, we will solve it. If this place gave us 50, and this place gave us 100, it's just an example. Then to get our resultant, resultant will now be 100, this one, divided by 50, and it will give us our resultant. But that is not where we are going to stop. We are not going to stop there. That is not where we are going to stop. We can't stop there. So our resultant will be there. To get the angle, it's just going to be tan inverse. Sorry, to get our resultant is not this. Our resultant is the square root, r square is equals to what we have here square, 50 square plus 100 square. And that's how, just the normal way we usually get our resultant. So that will be r square, sorry, that will be r square is equals to 100 plus what? 10,000. And then you find the square root and you get your r. Then to now get your direction, because you know that vectors have both magnitude and what? And direction. So what we have there is just the resultant. Then we have the direction. It will be tan inverse of the vertical component divided by the horizontal. So the vertical was 100, the horizontal was 50, and that's going to give us what? 2. It's just an example. That's not the values of what we have. I've just explained to us how we can resolve our vectors. Just explain how we can resolve our vectors. So let's go back to our board. So, and that's that. So we've resolved this. This one is declined at an angle 90. So that's why we could use the normal Pythagoras theorem, and this one that have the same starting point. You can see from here to this another example, solved example, and we get the same answer. So moment of a force and principle of moment. The moment of a force is the turning effect of the force about a point. You can see it's the pivot. It's the turning effect. It is equal to the product of the force and the distance. This is the force and the perpendicular distance between the pivots. So the moment of a force is the turning effect of the force about the point. It is equal to the product of the force and the perpendicular distance to the line of action of the force. So when you say moment of a force, it's just the force multiplied by the what? The perpendicular distance. The principle of moment states that when a body is in equilibrium, the total sum of anti-clockwise moment is equal to the total sum of the what? Clockwise moment. That is, clockwise moment is equal to anti-clockwise moment. And when the system is stable or balanced, it is said to be in equilibrium, as all the forces acting on the system cancel each other. They cancel each other because they are in equilibrium. The effect of movements is illustrated below. Yes, look at it in a rolling of a tap, opening, and the riding of the bicycle. So look at it, find the moment of 10 Newton acting at a perpendicular distance of 4 Newton. We already know that moment is force times perpendicular distance, and that is 10 times 4, and we have the 40 Newton per meter because force is in Newton, distance is in meter. Moment of a couple. A couple is a pair. Don't forget that. Pair, force, equal and opposite. You can see the forces, they are equal but opposite in direction. A couple is a pair of forces equal in magnitude whose line of action is not the same. Moment of a couple is equal to the product of either of the forces and the perpendicular. So we can choose because their magnitude is the same, but it is a couple. The magnitude is the same. So you can take anyone. You can say force times the perpendicular distance. So moment of a couple is equal to the product of either of the forces and the perpendicular distance between them. And its SI unit is also Newton meter because F is in Newton, distance is in meter. So that's the moment of couple formula. The applied force applied by the sum of the two arms of any two forces gives the moment of the force. Therefore, the moment of a couple of forces is provided by F multiplied by G, just like the moment of a force. Center of gravity. You can see these two children on the swing. They say a center of gravity, CG of a body, is defined as the point through which the line of action of the weight of the body always passes, irrespective of the position of the body. The line of action of the body always passes irrespective of the position of the body. What are the applications of the moment of couple? We have it scissors or wrenches. The process of churning of milk is carried out by applying the torque using the ropes that turns and rotates the handle. Concept of torque is also used in dams where water falling on turbines provide torque to rotate the shaft or the dynamo, which is used for generating electricity, and so on and so forth. So this is an example. This is an example of the application of torque. So a meter rule is found to balance at the 51 centimeter mark. So this is a meter rule, is found to balance at the 51 centimeter mark. So when a body of mass 70 gram is suspended at 10 centimeter mark, the balance point is found to be at 25 centimeter. So the thing is this, at the initial point, let's go to our board. Let's go to our board. So this is what it's trying to say. Don't forget what we talked about, center of gravity. This is a meter rule, right? This is a meter rule. And the balance point, when they put it on a pivot, it's balanced at 51 centimeter. It's balanced at this point, at the 51 centimeter mark. So after balancing that, but let's continue. Let's read the question. They said a meter rule is found to balance at the 51 centimeter mark. When a body of mass 70 gram is suspended at the 10 centimeter mark, the balance point is found to be at 25 centimeter. So look at it now. So when they now put here, now there was nothing on it. So later they now put something on it. What did they put? They put a mass at the 10 centimeter mark. This place is 10 centimeter. Don't forget, from here to the center was 50. So they now say they put what? A mass of 70 gram at the 10 centimeter. The mass is 70 gram. Don't forget that. Once they've done that, it's going to actually shift. Yes, it will shift. It's just like when two people are on a seesaw, on a swing. A fat person sits on one place. What will happen to the other side? The other side will go up. So what happened? The balance point changed. The balance point changed from where it was here. Now there was nothing there, and it's balanced there. Most times the body balances. The mass of the body is always at the center. The mass of this thing is always at the center. So look at that. They now said the balance point changed to where? To 25 centimeter mark. The balance point changed. So this is where the pivot is now, 25 centimeter mark. So if this place is 10, what will this place be? This place will definitely be what? It will be 15 centimeter, because they told us that it's now pivoted at 25 centimeter. So what is left from here to the where the mass of the body is? The mass of the body is always at the center, and we were told that this body balances at 51. So that is where the mass of the body will be. So what will be left here is just what? 51 minus what? Minus what is here. So look at it now. He said a meter rule is found to balance at the 51 centimeter mark. When a body of mass 70 gram is suspended at the 10 centimeter mark, the balance point is found to be at 25 centimeter. Find A, the mass of the ruler. The mass of the ruler will always be at the center. If you have a 100 centimeter meter rule, the mass of that meter rule is going to be at 50 if it's a uniform meter rule. But if it's not a uniform, they will tell you. So the mass is always basically at the center. So when they say we should find the mass of this meter rule, we are assuming the mass of the meter rule is what? At the center of the meter rule. Is at the center of the meter rule. So let's continue now. So look at it now. We have this place to be what? 25. And we know that from here to here is 51. So what is this place going to be left? If this place is 25, this place will be what? 26, right? This place will be 26. So here, so this place will be 26 centimeter. I hope we are getting that. This is the mass. The mass of anything. If you have 100 centimeter and they tell you that it's a uniform rule, you don't need anybody to tell you where the mass of that meter rule will be. It is constant. The mass must always be at the center. It's balanced. So that's the mass of the meter rule. So now, don't forget our formula. Clockwise moment is equals to what? Anti-clockwise moment. So AC anti-clockwise moment is equals to the clockwise moment, right? So 70 multiplied by 15 is equals to m, which is the mass of the body, multiplied by what? 26. So our mass will be equals to 70 multiplied by 15 divided by what? 26. And that is our mass. That is our mass. So look at it now. We've explained that, and that is what we have. 70 multiplied by 15 divided by 26 will give us 40.3 gram, 40.38 gram. That is the mass of the body. That is the mass of the body. So if we were to draw this before, this is how it's going to look like. This place will be what? 40.38 gram, which is the mass of the meter rule. The mass of the meter rule. And that is what is going to balance this other body is the mass of the body. And don't forget, look at it now, the force, when the force is big, what happens to the distance? The distance is small, because two of them are equal. If the force is small, the distance will be big, because it's perpendicular to each other, it's proportional to each other. It's the big force, small distance, small force, small distance, they are perpendicular. That's why it's force multiplied by the perpendicular distance. So we continue our this thing. He said our question, let the balance point be, okay, sorry, this is not the question. Then I said 2, the distance of the balance point from zero end if the body were moved to 20 centimeter mark. So now look at what has happened now. Look at what has happened now. We have this now. The body is now, this, the first time the mass was at 20 centimeter. Then I said, okay, we are now shifting this thing from 10 to where? To 20 centimeter mark. From 10 to 20 centimeter. So this is where they now put this 70 gram now. Don't forget, the mass of this body will still be at where? Will still be at 51. But we don't know where the balance point is now. We can't say that they did not tell us the balance. We don't know this distance, what the balance point is, and we don't know we don't know the difference between this place and this place. But the mass of the body is still at that 51, which is what? The mass of the body is now 40.38. It's now 40.38. That is the mass of the body. So how can we know what is at this point? And how can we know? We know that this place will just be 51, right? Minus the whole of this place is going to give us what the remaining part is. 51 minus x. If we assume that that place is x. So look at it now. From our diagram now, we already know that this part is going to be 51 minus x. Why? The other remaining part is going to be what? X minus what? Minus 20. X minus 20. So this part that has the mass is 51 minus, because we don't know what it is. So this small part now that we don't know is what? X. Minus 20. And this one is 51 minus x minus this part. It's going to tell us this point. So that is what we are going to use. So we're going to have 70 multiplied by what? X minus 20. Because they told us that this place is 20, but we don't know what this place is. Are you getting that? If this place, the balance point is 20 now. If the balance point was 20, sorry, this is the balance point. Okay, it was moved to 25 centimeters. We don't know what the balance point is. So it means this place minus what? Minus the 20 will give us what this part is. Will give us what this small part is. Then is equals to what? 51. The mass, which is what? 40.38 multiplied by what? 51 minus x. 51 minus this x will give us what? The distance between this balance, the mass, and the what? Balance point that we do not know. We do not know the balance point. So that is what we are doing. So m multiplied by 51 minus x is equal to 70 multiplied by x minus 20. You can see it here now. They shifted the mass to 20 centimeter. We don't know this place, right? And this is the balance point now. The mass is always at the center. So from here to this point, to where the mass will be multiplied, it's going to be that what's it called? The mass multiplied by the difference, because from here to here is 51. This small place is just what is remaining now is just 51 minus the balance points from the 20 centimeter mark. And so we have it as m times 51 minus x is equals to 70 multiplied by x minus 20. And when we do all our addition and subtraction, we have that our x here is what? 31.34 centimeter. 31, because it was shifted. Then this place, we don't know this place. So if this place is definitely x minus 20. It's going to give us what this place is. It's going to give us what that place is, because the mass of the distance of the balance point from zero. If the body were moved to the 20 centimeter mark, we shifted the body. So when you shift the body, then there is a pivot. We don't know where this body is now balanced, but we are sure of one thing: the mass is always at that 51. So it will be 51 minus this x. Then this point that we don't do, x minus the 20, will give us this balance point, and that was how we got our answer. Conditions for equilibrium of rigid body under the action of parallel and non-parallel forces. Algebraic sum of all forces must be 0. That's equilibrium. Ordinary sum of moments due to all forces about any point must also be zero. You must know all of this. Parallel forces acting on the rigid body in equilibrium must either act parallel to the length of the body intersecting its center of mass or act perpendicularly to its direction. Center of gravity and stability. The center of gravity affects the stability of objects. The lower the center of gravity is, the more stable the object. The center of gravity is a point in an object where the distribution of weight is equal in all directions and it does not depend on the gravitational field. We have stable and unstable neutral equilibrium. Stable equilibrium, when a particle is displaced slightly from a position, then a force acting on it brings it back to the initial position. It is said to be stable equilibrium. A body in stable equilibrium has low center of gravity and wide base. Yes, example, a marble placed on the bottom of a hemispherical bowl. Unstable equilibrium, when a particle is displaced slightly from its position, when a force acting on it tries to displace the particle further away from the equilibrium position, is said to be unstable. Unstable, can be displaced easily. A body in stable equilibrium has a high center of gravity and narrow base. A marble balanced on the top of a hemispherical bowl. You can see that now. You can see what they are trying to say. This is tendency to be in equilibrium. This is stable, this is unstable because it has acceleration, it can move, and this one is a neutral equilibrium. Neutral equilibrium, when a particle is slightly displaced from a position, then it does not experience any force acting on it and continues to be in equilibrium in the displaced position. It is said to be neutral equilibrium. And that is all today on our topic. Thank you on equilibrium of forces. Thank you. See you in our next